In early 1945, off the coast of Japan, an American F4U Corsair was forced to ditch after an engine failure during combat operations. The pilot ejected just as the fighter hit the cold Pacific waters. Within hours, Japanese patrol boats converged on the wreckage, recovering what would become one of the most significant intelligence finds of the war's final months. For nearly 3 years, Japanese pilots had encountered the American Corsair in the skies over the Solomon Islands, Rabaul, the Philippines, and now Japan's home islands. They had learned to respect its speed, firepower, and seemingly indestructible build. However, they had never before had an intact example to study, one they could measure, test, and fully understand the extent to which they had fallen behind. The story of Japan's encounter with the F4U Corsair is not just about a captured aircraft. It marks the moment when Japan's aviation specialists realized the full magnitude of American industrial and engineering superiority. By examining the Corsair, they would uncover truths about manufacturing precision, materials science, and design philosophy that shattered their assumptions about their own capabilities. The Corsair that Japanese salvage crews recovered represented the culmination of American fighter development. Designed in 1938 to meet the United States Navy's demanding specifications, the F4U evolved from a radical concept into one of the war's most feared combat aircraft. Its distinctive inverted gullwing, powerful Pratt & Whitney R2800 double WASP engine, and revolutionary performance made it instantly recognizable. More importantly, the Corsair achieved something that Japanese aviation struggled to match: a balance between speed, firepower, range, and structural strength. The origins of the Corsair can be traced back to 1938, when the Navy's Bureau of Aeronautics issued a request for a fighter capable of exceeding 400 mph in level flight. A revolutionary specification at the time, as most fighters could barely reach 350 mph. The Navy also demanded other qualities, including low stalling speed for carrier operations, a range of 1,000 miles, heavy armament, and bomb-carrying capability. Chance Vogt's response was bold. Chief designer Rex Basel and his team decided to build the aircraft around the largest, most powerful engine available at the time, the Pratt & Whitney R2800 double WASP. This 18-cylinder, two-row radial engine produced 2,000 horsepower, nearly double that of most contemporary fighters. To accommodate such power, the engineers designed an enormous 13-foot, 4-inch propeller, the largest ever fitted to a fighter. The engineering challenge was clear: how to provide ground clearance for such a large propeller, while maintaining the structural integrity needed for carrier operations. The solution became the Corsair's most distinctive feature: the inverted gullwing design. Instead of conventional straight wings, Basel's team created wings that angled downward from the fuselage before leveling out, forming a distinctive M shape when viewed from the front. This design allowed for short landing gear and provided the necessary clearance for the large propeller. The anhedral angle where the wings met the fuselage also optimized aerodynamics by minimizing drag. The prototype F4U first flew on May 29, 1940, piloted by Lyman Abelard Jr., VA's chief test pilot from the factory airfield in Stratford, Connecticut. On October 1, 1940, during a test flight between Stratford and Hartford, the F4U achieved a ground speed of 405 mph with a tailwind, making headlines as the first single-engine American fighter to reach this milestone. The aircraft's actual maximum level flight speed was 378 mph at 23,500 feet, still an exceptional performance for 1940. Production of the F4U Corsair began reaching operational units in late 1942. Marine Fighter Squadron 124 VMF-124 received the first combat-ready aircraft and deployed to Henderson Field on Guadalcanal on February 12, 1943. However, the Corsair's combat debut was far from successful. On February 14, 1943, during the battle known as the St. Valentine's Day Massacre, the Corsairs suffered a disastrous first engagement. 9 American aircraft were lost, including 2 Corsairs, along with several P-38 Lightnings, P-40 Warhawks, and bombers. In contrast, the Japanese defenders lost only a single Zero fighter. The 91 loss ratio in Japan's favor was so severe that daylight bombing missions to Bougainville were suspended for tactical reassessment. This engagement showed that superior technology alone could not guarantee victory. Tactics, experience, and proper deployment were equally important. American pilots quickly adapted. They discovered that the Corsair's strengths lay not in dogfighting, but in a tactic known as boom and zoom. While the Corsair could not maneuver a Zero in slow, speed turns, it could dive, climb, and outrun any Japanese fighter. The key was maintaining speed and altitude, diving on enemy aircraft, firing, and then using superior speed to disengage before the enemy could react. Second Lieutenant Kenneth A. Walsh of VMF 124 became the first Corsair ace on May 13, 1943, mastering these tactics and eventually achieving 21 aerial victories. As the war progressed through 1943 and 1944, the Corsair's reputation grew. Marine squadrons in the Solomon Islands, flying from makeshift coral airstrips, exploited the aircraft's ruggedness to devastating effect. The Corsair proved capable of absorbing battle damage that would have destroyed lighter Japanese fighters. Its 6 50-caliber Browning machine guns, 4 inboard guns carrying 400 rounds each, and 2 outboard guns carrying 375 rounds each, totaling to 350 rounds, provided overwhelming firepower. Later variants like the F4U-1C replaced the machine guns with 420 mm cannons, though many pilots still preferred the reliability and higher ammunition capacity of the 50-caliber guns. The Corsair's versatility extended beyond air combat. By mid-1944, Corsairs were regularly carrying external ordnance, 1,000-pound bombs on the center line and wing racks, 8 5-inch high, velocity aircraft rockets or napalm canisters. This fighter-bomber capability made the Corsair invaluable for close air support during amphibious operations. During the Okinawa campaign in 1945, Corsairs flew thousands of ground attack sorties, earning the nickname Angels of Okinawa from grateful infantrymen. What Japanese pilots encountered in combat only told part of the Corsair's story. From the cockpit of a Zero or other Japanese fighter, a pilot faced an opponent that was faster, stronger, and more resilient. However, to truly understand the engineering and manufacturing techniques behind these advantages, a physical examination of the aircraft itself was necessary. Japan's capability for such technical analysis was centered around 2 key facilities: the Yokosuka Naval Air Technical Arsenal, south of Tokyo, and the Army Aviation Technical Research Institute at Tachikawa. These organizations had been examining captured Allied aircraft throughout the war, recovering examples from battlefields across the Pacific. Their work provided valuable intelligence about American capabilities, but most captures were damaged aircraft or incomplete wrecks salvaged from crash sites. An intact, operational example of a frontline American fighter, such as the Corsair, was an extraordinary opportunity. The Japanese Navy's Yokosuka facility had been conducting technical research since April 1, 1932, when it was reorganized as the Kaigon Kokusho Naval Air Arsenal. By World War II, Yokosuka employed thousands of engineers, designers, and technicians. The arsenal was responsible for designing many Japanese naval aircraft, although production was contracted to companies like Aichi, Nakajima, and Mitsubishi. Yokosuka's engineers were highly skilled and understood aircraft design at the highest level. When a salvaged Corsair arrived at Yokosuka in early 1945, it represented one of the most modern American fighters, recovered in relatively intact condition. Although the aircraft had suffered water damage during its forced landing, the basic structure remained intact. Recovery teams had worked to prevent the Corsair from sinking completely, and it was transported to Yokosuka's secure technical area for detailed examination. The initial assessment focused on the overall condition of the aircraft. Despite saltwater immersion, much of the Corsair remained intact. The massive Pratt & Whitney engine required complete disassembly and cleaning, but the airframe showed no combat damage. This was crucial, as previous Allied aircraft captures often involved heavily damaged planes, making it difficult to distinguish design features from battle damage. The Japanese specialists began their examination with systematic photography and measurement. Every dimension of the aircraft was recorded. The wingspan was 40 feet 11.7 inches, the length was 33 feet 4 inches, and the height was 15 feet with the wings extended or 16 feet 2.3 inches with the wings folded for carrier storage. The inverted gullwing design immediately drew attention. Japanese designers understood the aerodynamic and structural advantages of this configuration, but they also recognized its manufacturing complexity. Creating the compound curves and maintaining precise angles required sophisticated tooling and quality control. Capabilities beyond what most Japanese factories could achieve reliably at this stage of the war. The examination revealed something that particularly surprised the technical team. Despite the Corsair's advanced design, portions of its outer wing surfaces were covered with fabric rather than metal. After inspecting the main wing spar and armament bays, the Japanese aviation specialists were surprised to find that both the upper and lower wing surfaces, as well as the control surfaces, ailerons, elevators, and rudder, were covered with fabric. At the time, most modern fighters by 1944 to 1945 were constructed entirely from metal. This discovery initially puzzled the Japanese team. Further analysis revealed that the fabric covering was a deliberate design choice made during the Corsair's development between 1938 and 1940. The use of fabric reduced the aircraft's weight in areas where structural loads were minimal, allowing aluminum to be reserved for the critical load-bearing components. The fabric was specially treated to provide adequate strength and weatherproofing, while weighing significantly less than metal skinning. This approach demonstrated a mature understanding of resource allocation for optimal performance. Disassembling the wing structure revealed construction methods that were both impressive and concerning for the Japanese engineers. The main wing spar, the critical structural element responsible for carrying flight loads, was a massive forging of exceptional quality. American metallurgy had produced aluminum alloy forgings with strength characteristics that Japanese facilities struggled to match. The spar's dimensions and load-bearing capacity exceeded those of comparable Japanese fighters. This single component highlighted a fundamental difference. American industry was able to produce large, complex forgings with consistent quality, whereas Japanese manufacturers increasingly relied on built-up structures assembled from smaller components. The internal wing structure also demonstrated a high level of sophistication. The aluminum ribs stamped from sheet metal showed remarkable precision and consistency. Each rib was virtually identical to the next, indicating manufacturing processes with tight quality control. In contrast, Japanese aircraft production increasingly struggled with consistency as the war progressed, with individual aircraft showing variations in component quality. Attention then shifted to the Corsair's armament installation. The 6 Browning AN-M2 .50 caliber machine guns mounted in the wings represented formidable firepower. The installation was compact, reliable, and designed for ease of maintenance. What struck the Japanese examiners was not just the firepower, but the completeness of the armament system. Ammunition boxes, feed systems, spent cartridge ejection, and charging mechanisms were all engineered to work seamlessly together. The guns themselves were examples of precision manufacturing. American ordnance production had reached a level of reliability that Japanese industry envied. The Browning M2 machine gun was a mature design, perfected through decades of development, and manufactured by the millions with extraordinary consistency. Japanese technicians examining these weapons recognized manufacturing techniques and quality standards their own factories could not consistently achieve. The discovery of 150 pounds of armor plate protecting the cockpit, along with a 1.5-inch thick bullet-resistant glass panel behind the windscreen, reinforced the Japanese team's impressions of American design philosophy. Japanese fighters had largely abandoned heavy armor protection in favor of lighter weight and better maneuverability. The early success of the Zero seemed to validate this approach. However, as American fighters grew more powerful and better armed, the lack of protection became increasingly fatal. The Corsair demonstrated that it was possible to incorporate substantial protective armor without sacrificing performance, thanks to the immense power of the R2800 engine. The engine was the centerpiece of the technical examination. The Pratt & Whitney R2800 Double Wasp was a peak example of American aero engine development. With 18 cylinders arranged in 2 rows of 9, it displaced 800 cubic inches and produced over 2,000 horsepower, making it a mechanical masterpiece. While Japanese engineers had encountered this engine in captured aircraft before, they had never had a relatively intact example for thorough analysis. The engine's construction revealed manufacturing capabilities that were almost incomprehensible. The cylinders were precisely machined with tolerances measured in thousandths of an inch. The pistons, connecting rods, and crankshaft components displayed surface finishes and dimensional accuracy that Japanese engine manufacturers struggled to achieve. The two-stage supercharger system, designed to maintain power at high altitudes, featured complex internal passages and precisely fitted rotating components. Japanese attempts to develop comparable supercharger systems had largely failed due to manufacturing limitations. Perhaps most impressive was the engine's reliability and power output. American radial engines routinely produced their rated horsepower for hundreds of hours between overhauls. In contrast, Japanese engines, even new ones, often failed to meet their theoretical power ratings and required frequent maintenance. The consistent performance of the R-2800 came from superior metallurgy, better lubricants, more precise manufacturing, and more sophisticated quality control. The propeller system was equally revealing. The Hamilton Standard hydrostatic propeller, with its 13-foot 4-inch diameter and variable pitch capability, represented advanced aerodynamic design and hydraulic control systems. While Japanese engineers understood propeller theory, they lacked the manufacturing facilities capable of producing large propellers with the necessary precision. Examination of other systems throughout the Corsair revealed consistent patterns of excellence. The landing gear mechanism was complex but precisely manufactured. The cockpit instrument panel offered a comprehensive array of gauges and controls, surpassing anything seen in Japanese fighters. The fuel system incorporated self-sealing tanks made of multiple rubber compound layers that swelled when punctured, preventing catastrophic fuel loss. Technology largely absent in Japanese aircraft. The electrical system powered extensive equipment with high-quality wiring, proper insulation, and well-organized components. Perhaps the most revealing aspect was the overall quality of materials and manufacturing. Every component, from major structural elements to small fasteners, displayed consistent quality. The aluminum alloys had uniform properties, the steels were properly heat-treated, and the surface finishes were smooth and professional. The aircraft felt substantial, well-made, and built to last. This level of quality stood in stark contrast to Japanese aircraft production in 1945. Wartime shortages had forced Japan to rely on substitute materials. The quality of aluminum had deteriorated, skilled workers had been conscripted, and factories operated under the constant threat of American air raids. As production schedules prioritized quantity over quality, quality control suffered. The examination of the captured Corsair took place at a time when Japan was facing imminent defeat. American B-29 bombers were systematically destroying Japanese cities. The Navy had been decimated at Leyte Gulf. The Philippines had been liberated, Iwo Jima had fallen, and Okinawa was under assault. In this desperate context, the Corsair examination took on a somber significance. It was no longer about intelligence gathering for future victories, but a final reckoning with technological reality. Japanese engineers at Yokosuka and Tachikawa wrote detailed technical reports documenting their findings. These reports included measurements, descriptions of manufacturing techniques, and assessments of American capabilities. While the tone was professional, the underlying implications were clear in nearly every category. American technology surpassed Japanese capabilities. The gap was not small or easily closed. It represented years of industrial development, massive investments in research and tooling, sophisticated supply chains, and resources that Japan simply did not have. By the war's end in August 1945, at least 2 Corsairs had been captured by Japanese forces. Evidence suggests that technical personnel made attempts to repair at least one aircraft to flying condition, as photographs show captured Corsairs with patched wings and fuselages. While it remains uncertain whether the aircraft were flight tested, these repair efforts indicate serious attempts to make the aircraft operational for evaluation. When American occupation forces arrived at the Yokosuka Naval Air Technical Arsenal in September 1945, they discovered extensive evidence of Japan's technical intelligence efforts. Captured Allied aircraft were scattered across the facility, and technical reports, drawings, and photographs documented Japanese attempts to understand Allied technology. American intelligence officers collected the materials recovered from the captured Corsairs, recognizing their value for understanding what Japan had learned. The story of Japan's examination of the F4U Corsair goes beyond technical intelligence. It represents the vast gap that separated American and Japanese aviation by the end of the war. When the Corsair first entered combat in early 1943, Japanese pilots flying Zero fighters could still compete effectively, relying on superior tactics and pilot skill. However, by 1945, even experienced Japanese pilots in more modern aircraft had little chance against well-flown Corsairs. The Corsair's technological advantages, combined with overwhelming American numerical superiority and better pilot training, created nearly impossible odds for Japan. The Corsair achieved an official kill ratio of 11:1 against Japanese aircraft. American pilots flying Corsairs shot down 140 Japanese planes while losing only 109 Corsairs to enemy action during World War II. These numbers reflected not just the Corsair's technological superiority, but also the overall advantages of the American war machine: better training, superior logistics, overwhelming production capacity, and advanced technology at every level. Japanese engineers examining the captured Corsair understood this disparity. They could measure the performance gap, analyze the differences in manufacturing, and assess the resource imbalances. Their reports documenting these findings stand as acknowledgments of Japan's failure to match American industrial power. The Corsair itself went on to serve well beyond World War II. It fought in the Korean War from 1950 to 1953, proving effective in ground attack and close air support roles, even as jet fighters began taking over air superiority missions. Foreign air forces, including France, used the Corsair in colonial conflicts through the 1960s. The last combat missions by the Corsair occurred in July 1969 during the brief Soccer War between Honduras and El Salvador. On July 17, 1969, Honduran Captain Fernando Stu, flying an F4U-5, shot down 3 Salvadoran aircraft, including 2 FG-1D Corsairs. The final combat victories for the type. Ironically, these victories were achieved against other Corsairs. From its first flight in 1940 to its final combat missions nearly 30 years later, the Corsair proved to be one of the most successful and long-lived fighter designs in aviation history. For Japan, the encounter with the Corsair was part of a larger reckoning with technological reality during the American occupation. Japanese engineers and scientists, who had struggled with material shortages and industrial limitations during the war, now worked alongside American occupation authorities to rebuild Japan's industry. The lessons learned from examining American technology, including the Corsair, would influence post-war Japanese manufacturing philosophy. The emphasis on quality, precision manufacturing, and continuous improvement that defines modern Japanese industry can be traced back to the hard lessons learned when Japanese engineers studied what American industry was capable of. The Corsair, recovered in early 1945, symbolized more than just a downed fighter. It was proof of engineering excellence and manufacturing sophistication that Japanese aviation had long sought throughout the war. The lessons it provided came too late to alter the outcome of the war, but they played a significant role in shaping the post-war peace. In studying this American fighter, Japanese engineers confronted the full scale of the challenge Japan had faced. While they fought with courage and skill, those qualities alone could not overcome the massive technological and industrial advantages held by their opponents. The story ends not with victory, but with acknowledgement. Japanese technical reports on the Corsair, discovered by American occupation forces and now preserved in archives, stand as silent witnesses to a moment when one nation's engineers recognized the full extent of another nation's capabilities. The Corsair they examined has long since disappeared, likely scrapped during the chaotic post-war period, but its legacy endures in the lessons it imparted about what technology, when applied with the right resources and manufacturing sophistication, could achieve. Japanese aviation would rise again in the post-war era, but never again would Japanese engineers underestimate what their American counterparts could accomplish when they had the industrial capacity, scientific knowledge, and resources to fully realize their designs. The examination of the F4U Corsair by Japanese technical personnel in 1945 marks a pivotal moment, the point at which Japan's aviation establishment fully understood the technological chasm that had developed during the war. This lesson wasn't written in propaganda or combat reports, but in aluminum alloys, precision forgings, and manufacturing tolerances that spoke louder than any words could about the true power of American industry.